Since the beginning of Sensing the Universe series, we've done deep dives on many sensors and systems which were carried on various probes to location throughout the solar system. Although these systems were custom-made for their respective missions, they were more or less mobile space-based adaptations of sensors and systems that we use in labs on Earth. Some of these outstanding systems that were featured in the past were Cassini's Cosmic Dust Analyzer, Solar Orbiter's Solar Wind Plasma Analyzer, and Tianwen-1's Ground Penetrating Radar. Every so often, a sensor or a system needs to be built to a precision and physical tolerance that is higher than anything we've created in the past. In these situations, more often than not, we have to also develop new ways of manufacturing the parts and testing them. The primary mirrors on the James Webb Space Telescope, along with its active optics, is a good example. The James Webb Space Telescope was launched in December of 2021. There's an equally fascinating sensor that was also launched into space, but 17 years earlier in 2004. The sensor was a gyroscope, and the mission was called Gravity Probe B. Its goal was to directly measure the curvature of space-time and look for an effect called frame dragging in this part of our universe. The operational principle of Gravity Probe B is quite simple. Place a gyroscope in space, but still close to the Earth. Spin it up, and then point it at a reference star. If we can eliminate or minimize all of the forces that can potentially affect the gyroscope, then it will remain pointed at the reference star for a long, long time. However, if frame dragging is true in the vicinity of Earth because of its spinning mass, then the gyroscope will drift from the reference star by a certain amount in a year. Since there are no other forces affecting the gyroscope, the measured drift must be due to the twisting of space-time itself, especially when the amount of the drift matches what's predicted by general relativity. But here's the catch. As stated before, the gyroscope should not be affected by any force once it's spinning and pointing at the reference star. That includes forces of gravity, forces from the spacecraft that's hosting the gyroscope, forces from air movement, forces from any magnetic field, forces from direct solar or indirect solar radiation, and finally, contact forces from the detector that will actually measure the drift. Suddenly, this simple concept has turned into an engineering nightmare. Like so many scientists have said, the main limitation to our understanding of our world is how sophisticated we can make our detectors. And with Gravity Probe B, we've pushed that limit further. At the very core of Gravity Probe B is a set of spherical, near-perfect gyroscopes. What does that mean? It means a gyroscope that is perfectly balanced when it spins. This means that the density is extremely uniform and that the shape is almost a perfect sphere. This is extremely important because a non-uniform density and a sphere that is not extremely smooth will introduce vibration in the sphere as it spins, vibration that will cause its spin axis to drift. To prevent this, each sphere, which is the spinning part or the rotor of the gyroscope, is carved from a single specially grown quartz crystal. The quartz is then baked, which turns it into fused quartz. Fused quartz has a very low coefficient of thermal expansion, meaning that it doesn't expand much as its temperature changes. This is important since we need to keep the density and shape constant throughout the experiment. The fused quartz is finally shaped into a near-perfect sphere. The size of the sphere is 3.8 centimeters in diameter. But if you could enlarge the sphere to the size of the Earth, the tallest mountain and the deepest trench in the ocean would only be about 2.4 meters. That's how smooth and perfect these spheres are. Okay, so now we have a spherical rotor of the gyroscope which can spin at about 4,000 RPMs. But how can we spin the sphere without making mechanical contact with it? Any mechanical spin on the sphere will most likely damage the sphere and would require an elaborate engagement and disengagement mechanism. In addition, it would also require making a hole in the housing that contains the gyroscope. This is not going to work out, given the gyroscope's precision we are working towards. So instead of a mechanical spin, the spinning of the sphere is done with a gas. Helium gas is used in many applications when we need a gas to do some work, but we don't want the gas to chemically react with the items that the work is applied to. In addition, because its atomic size is very small, it can diffuse easier than most other gases. This helps in making sure that after spinning up the sphere and then evacuating it, that no residual helium gas remains in the housing, which could potentially slow down the sphere. We go through great lengths to avoid touching the sphere by using pressurized helium to spin it. The question is, how can the sphere stay in place and rotate without the helium blowing it onto the inner walls of the casing? The solution is to use electrostatic suspension. Inside the gyroscope casing, there are 6 metal discs that provide the electrostatic field, and in the center is the quartz sphere. However, this still wouldn't work to keep the sphere away from the walls, because all electrostatic fields that are set up to attract or repel an object placed between the fields are inherently unstable. The gyroscope electronics solves this issue by monitoring the distance from the surface of the sphere to the 6 electrostatic plates. This distance is measured by measuring the capacitance that exists between each of the 6 plates and the sphere. The further away the sphere moves away from the plate, the lower the capacitance becomes, and vice versa. Based on this data, the electronics will adjust the electrostatic force on the sphere to keep it away from the inner walls of the casing by just 33 micrometers. That's less than the thickness of a piece of paper. Now we have a super smooth sphere that's spinning at high speed and nothing is in physical contact with it. Our new question now is, how can we see the direction that the spin axis is pointing to? After all, that's the main parameter that we're measuring on Gravity Probe B. In a stereotypical gyroscope, it's easy to see the spin axis and its direction. But with a near-perfect sphere, that is impossible, because any markings we put on the sphere will make it not as smooth as required for the experiment. However, if we apply the markings uniformly over every exposed surface of the sphere in a really thin layer, then we could retain the smoothness of the sphere. But then again, it would be useless as a marking because it's everywhere. It may as well be a coating. Now, depending on the material of this coating, it could actually be useful in determining the direction of the spin axis. So knowing this, the quartz sphere in the gyroscope was coated with a special material, niobium. Niobium is a high melting point metal and a high temperature superconductor. High temperature in this case is anything above minus 196.2 degrees Celsius. So it still requires a really cold environment for the superconducting properties to take effect. The quartz sphere in the gyroscope is coated with this metal to a thickness of 1.27 micrometers. So how does this coating help us determine the spin axis of a near-perfect sphere without a marking? Fritz London, a theoretical physicist from the early 20th century, discovered that when a superconducting metal sphere, solid or hollow, spins, it creates a magnetic field. This effect is called the London moment. The axis of this magnetic field created lines up exactly with the physical spin axis of the rotating sphere. If we can detect the orientation of the magnetic field, we could now detect which direction the gyroscope is pointing and then track any drift. The strength of the magnetic field is detected with a device called SQUID. It's an acronym that stands for Superconducting quantum interference device. It has the ability to measure very weak magnetic fields. The magnetic field created by the spinning sphere is very weak. That's why a squid is required, instead of an ordinary magnetic field detector that relies on the Hall effect, for example. The squid doesn't immediately detect the axis of the magnetic field. Instead, over a few orbits around the Earth, this axis can be determined by how the magnetic field strength detected by the squid varies during each orbit. We finally have a gyroscope sphere that will maintain its spin axis as the spacecraft orbits the Earth. The final thing we now need to do is to find a reference point in space and then align our gyroscope to it, tracking it for a year. When we look out into space using visible light, we see stars, planets, moons, and asteroids. Whatever reference point we choose has to be fixed in space relative to Earth. In order for a celestial body to appear fixed in space, it has to be at a great distance, at least hundreds of light years, to avoid the parallax effect when viewed from Earth as it orbits the Sun. Since direct observations of planets, moons, and asteroids are not possible at such great distances, we can only use stars as possible reference points. The guide star that was used by Gravity Probe B was IM Pegasi, but even at 329 light years away from Earth, the parallax motion from Earth would still be too big for the Gravity Probe B experiment. If the parallax motion could be compensated for, then IM Pegasi could still be useful as a guide star. Aside from visible light, IM Pegasi also emit microwaves. Using multiple large radio telescopes, the position of IM Pegasi could be determined relative to distant quasars. A quasar is an extremely luminous active galactic nucleus and are some of the most distant celestial bodies from Earth, with the nearest one being 500 million light years from Earth, and the furthest one over 10 billion light years away. These bodies are the true static reference points in space. But these enormous distances also makes them very, very dim, and thus invisible to the optical telescopes onboard Gravity Probe B. So, by using the microwave emission from both guide star and quasar, we can get the motion of the guide star relative to the ultimate reference point, a quasar, and then subtract that from the observed position of the guide star to get its true position and eliminate the parallax effect and other virtual motions. Tracking the guide star should be relatively easy. Just keep the star in the middle. This would be straightforward if the star appeared like a true geometric point inside the telescope. In reality, it appears as a disk with faded edges. This makes it not so trivial to detect the exact center of the disk. The telescope of Gravity Probe B has a module called Image Divider and Detector Assemblies. Its job is to detect the exact center of the light disk from the guide star. First, the incoming light is split into two by a beam splitter. Each beam is then focused on a specific type of prism called a roof prism. The prisms are aligned on the vertical and horizontal axis. They each split the half beam into two, and the intensity of each of those beams are detected by a light detector. If the incoming light is centered on the axis of each prism, then each light detector will detect the same intensity. This indicates the telescope is pointed directly at the center of the star. If the detectors don't have all the same intensity, then the alignment is off. The alignment electronics uses this difference in intensity to turn the telescope until all sensors detect the same intensity, meaning the telescope is aligned with the guide star. This system was able to align the telescope to within 1 milliarc second from the center of the star. 1 milliarc second is so small that if you were to walk on a slope at that angle for 1,000 kilometers, you would gain a height of only half a centimeter. There's one more issue we have to address to make Gravity Probe B ready to test Einstein's frame dragging aspect of general relativity. we have to eliminate all forces that would affect the operation of the gyroscope. That includes forces created by temperature, pressure, magnetic field, and acceleration. The gyroscope, which depends on the London moment to be measured properly, depends on the superconductor property of the spinning sphere. This property comes into effect only at a very low temperature, minus 271 degrees Celsius. This low temperature is also important in keeping the fused quartz component, like the gyroscope and the telescope, from thermally expanding at different rates. Even though objects in orbit around Earth can get cold over a period of time, that's only when they're in the shadow of the Earth. And even then, they are slightly heated by the heat coming from the Earth. When the object leaves the Earth's shadow and goes into direct sunlight, its temperature will rise very quickly unless it's well insulated. To make sure that all of the science instruments are at a low temperature of minus 271 degrees Celsius, they are placed inside a tube which is surrounded by 2,300 liters of liquid helium at that same temperature and sits inside a giant Dewar flask. The flask is also covered with a multi-layer insulator to help prevent the liquid helium from heating up. However, over time, some of the liquid helium will have absorbed some heat and be turned into gas. At that point, the heated gas will be vented from the spacecraft to prevent it from heating the remaining liquid helium. More on that later. In order to reduce the gas pressure surrounding the spinning sphere to near zero, special vents are opened to vent out the helium gas that was used to spin up the sphere. Furthermore, the temperature surrounding the gyrosphere is temporarily increased from minus 271 degrees Celsius to minus 267 degrees Celsius to vent out any gas that was adsorbed by the gyroscope. To prevent the gyroscope from being affected by magnetic fields, it's also surrounded by 4 lead bags. While we think of the Gravity Probe B experiment as the spacecraft is carrying a spinning gyroscope sphere around the Earth, in reality, the spacecraft is matching the trajectory of the sphere, which is in free fall around the Earth. The spacecraft adjusts its trajectory to match that of the sphere by using its 4 small thrusters for attitude and translational control. The thrusters are powered by helium gas, the helium gas that was vented earlier when some of the liquid helium started to get too warm. So now, everything has been accounted for to ensure that the 1-year mission of collecting data on the shape of space-time near the spinning Earth will be as accurate as possible. From that data, we will then be able to see directly if frame dragging around spinning objects is real. In 2011, the data collected by Gravity Probe B confirmed the existence of frame dragging around massive rotating objects. Prior to this report, the raw data that was received had many unexpected signals embedded in it, making it hard to filter out the actual gyroscope drift data. In particular was the electrostatic polarity that existed on the rotating sphere. This was caused by the uneven application of multiple coatings of niobium on the sphere. Since the sphere spins, the electrostatic polarity created a magnetic field which affected the spin axis of the sphere. Despite this and other issues with the gyroscope, scientists were able to create models of these errors, and based on these models, they were able to subtract the majority of the errors from the raw data. There are many scientists that still have low confidence in NASA's final conclusion on the accuracy of Gravity Probe B because of the accuracy of these error models. So, at worst, the result of Gravity Probe B is inconclusive, and at best, frame dragging was detected as the general theory of relativity predicted. Better error modeling or better instruments may give us a more conclusive answer in the near or far future. That, however, may depend on whether or not we're near a high-speed spinning massive mass. I'm DexDFX for Sensing the Universe.